Let's talk about the length of a parametric curve. So to compute the arc length of a parametric curve, you integrate from alpha to beta. These are your time values of this formula right here. Square root of the x formula's derivative squared plus the y formula's derivative squared. And I wrote total here just to remind you that this will compute, like if the curve is tracing over itself several times in this time interval, it's going to be counting every time. So you generally want to make sure that the path is only done once in that time interval that you choose for the bounds. All right, so let's do an example. In this example, we're asked to find the length of the curve given by these two parametric equations over the time interval 0 to pi. All right, so for each of these, the x prime and the y prime are going to require a product rule. So I'm going to do those as separate tasks at the beginning. So if x of t is e to the t, cosine of t, then its derivative will use the product rule. So f prime g plus g prime f prime g plus g prime f, right? And then we also have y of t, very similar. Our product rule derivative is f prime g plus g prime f. And of course, the order of these terms can change. Okay, so all together we have arc length equals the integral from 0 to pi square root of, this is going to be pretty big for a while, this x prime derivative squared plus this y prime squared. dt. Okay, so now we need to start actually squaring things out and simplifying. Before I square anything out, I'm going to pull out these e to the t terms since they're everywhere. So this e to the t and this e to the t. I can think of this as e to the t squared cosine minus sine squared. And then same thing here, we can pull out the e to the t and square it on its own. And we're left with sine plus cosine squared. Okay, so what that gives me, we still have the integral 0 to pi. Each of these has an e to the t squared. So I'm going to factor it out of everything. And we'll simplify that down in a future step. Okay, so now we have cosine minus sine squared. That will be cosine squared minus 2 sine cosine plus sine squared. Sine plus cosine squared is very similar. It'll be the exact same expression, but with a plus sign between all of the terms. Okay. And now we have, thank goodness, a great deal of cancellation. So for one thing, I have minus 2 sine cosine plus 2 sine cosine. This cosine squared plus sine squared combines to 1. And then this cosine squared plus sine squared is another 1. So we have the integral 0 to pi square root of e to the t squared is e to the 2t, and then times 1 plus 1. Okay, much better to look at. We're almost there. All right, so of course, 1 plus 1 is 2. And then we also have e to the 2t under the square root is going to cancel out the 2. So the most simplified we can write this is e to the regular t outside of the square root, and then the 2 is still under the square root. Now the antiderivative step is pretty straightforward. We'll plug in each of our bounds. And of course, e to the 0 is 1, so our final answer will be root 2 e to the pi minus root 2. That'll be the length of the curve created by these parametric equations over this time interval.